So we were looking at rearranging formula last time. There's some key points that we're bringing out last time, and we talked about rearranging for I. So can you remember what we do to rearrange Ohm's law for I? Divide both sides by R. Yeah, so the key thing is that if we divide one side by R to get rid of it, we must do the other. And that's the key thing, which you can apply to any formula when you have to rearrange it. So this means we can now cancel out the R's and we're left with I equals V over R. Okay? So rearranging formula we were talking about last time is the idea of reversing the process to rearrange, undo what you did last first. Okay? So we were talking about thinking about the story of what happened to the formula, thinking about what's the last thing that happened to it and then undoing it, and then so on and so on until we end up with what we want. Something else we mentioned, if the denominators are the same, you can put them together. So V over T minus U over T equals V minus U all over T. And whatever you do to one side, you must do to the other. And someone pointed out that multiplying by 1 over 2 pi is the same as dividing by 2 pi. Thinking about those things being the same thing is useful. So those are some of the general points that we're making. What was the last about? Use engineering notation. Right. Okay, so yeah. Are you familiar with that now? Is that's the general point? Yeah, okay, right. So we're all happy after last week. Any questions raised their ugly heads between last week and this week? Okay then. Rearrange that formula for me then. Without looking at last week's notes, because we've done this already, just tell me what to do. You probably won't need to write this down because you've got it written down. So let's just look at it. I want to rearrange for H. So what are we going to do, Matt? Right. P pressure. That symbol rho. Yeah, correct. Divide both sides by rho G. Divide both sides by rho G. So then I can cancel out the rho and the G on the right hand side. And I've got the formula. P equals, H equals P over rho G. So that symbol there is rho, Matt. R-H-O. Right. Remember this one? Let's see if we can suss it between us without looking at what we were doing last week. Try not to look at that. Okay? Yeah, so what's the first thing I'm going to do? I want to get what on its own? I haven't said. L. L on its own. If I were to try and get rid of the G, it's inside the square root then, so it's probably not a good idea. First thing to get rid of. Yeah, times by the 2 pi. Remember to get rid of it, and that sort of brings us back to that previous thing. Multiplying by 1 over 2 pi is the same as divide by 2 pi. So how do I get rid of divide by 2 pi? Multiply by 2 pi. So what I'm going to write equals. Okay. So next, what are you, Alfie? Square everything, right. So how am I going to write it on the left-hand side? Right, yeah. I actually don't like to see the number in the middle, so I'm going to put the number first, t, 2 pi times t, because I like to see it that way around, squared equals L over G. Yep, and finally, times by G, and we've got L. Okay, so it's that sort of process that we were talking about last week. L equals G times 2 pi t squared. Okay. So if G, which it does, is 9.81 newtons per kilogram, that's what that equals. If T was 1.6 times 10 to the minus 3 seconds, calculate L for me on your calculator in one hit. So answer 0.991 times 10 to the minus 3 or 991 times 10 to the minus 6 meters. Are they the same thing? Yes. Yeah. They are the same thing, Tom, because minus 3 in this top one means I've got to have to go back 3 places. Agreed? To get it to where it should be. So if you look at this one, the decimal point is actually there. So to get it to there, I've actually got to go back 6 places. So that's the same as that. And they're both in meters. There are meters. What gives it the fact that it's meters? It's to do with this, actually, because newtons and kilograms and meters all go together. So how do I know it's in meters? Because of this unit here. No, no. Kilogram is the base unit. So kilograms goes with meters, goes with seconds, generally. Ah, true. I understand what you're saying there, but the basic unit of mass that goes with the Newton is the kilogram, not the gram. I can see why you might think it would be the gram, but it's the kilogram. Yeah. Okay. Right. So what we're going to do today then, let's have a look at the aims for today then. So I've got some things in mind to do today. One is to look at the function. And its use in engineering. And then I want to think about the algebra around rearranging functions. So I want to talk a little bit more about rearranging functions. And finally, I want to look at the equation. Looking at forming and solving. So that's what I want to do today. Okay, so this first thing, the function, I just want to sort of introduce you to the way we can represent functions and describe functions and a notation for it, and discuss how it's used in engineering, in modelling in particular, because over the next couple of years we'll be sort of moving towards looking at using functions to model engineering situations. So in the final year you'll be doing some of that sort of work. You can't manipulate functions and rearrange formulae and solve equations without some algebra. So we'll be looking at a bit of algebra, reminding you of some algebra. And I'll be pointing you at where to look in the textbook to practice the skills. And then we'll look at the equation. Lots of times in engineering you form an equation, and then once you form the equation you've then got to solve it to get the unknown. Okay, so that's the idea. So first of all, let's look at some functions. So here's a function. Well, fx equals ax to the n. Actually, thinking about it, let's change that letter. Sorry. I don't want that to confuse you, because it's not as though we always use f because f means function. We can use any letter we like. So it's not the fact that it's that it's the f that's important, it's the fact that this describes a function. So this is what we call the independent variable. X. So immediately we know that x is the independent variable over here. Therefore, any other letter that appears here must be constant. So n is a constant. We don't know what it is, but it's not changing. A is a constant. We don't know what it is, but it's not changing. So there's our function. And we can think of it in many different ways. One way is like a function machine. So we have an input, a function machine, and an output. So in and out for like a computer. Okay, you put a value into a computer or a calculator, and out comes the result. So in is our x. A function in this case is what we do to it. So the g function, if you like, is you multiply whatever your input is by you find x to the power n, whatever n is, and then you multiply that solution by a. So you do that to the function and out comes the result. So for example, if I had x equals to 2 going in, so I had an input of 2, I would also have to set my constants. So if this was some sort of computer or something, I'd need another 2 inputs into this function machine, one for the constant a and one for the constant n. So let's say a equals 4 and n equals 2. So now we've got all the information we need. What's the output? 16. Right. Okay. Everybody happy with that? Alpha, yeah? So that's one way of thinking about this function as a machine, and that's like the input. X is the variable, or the independent variable that we're going to enter, and then if we enter that value, we get. So how would we write this? Gx, whoops, we've had gx equals, so if I wanted to know what g was for a particular value, I'd say g for 2. So that would mean I'm going to let x equal 2 equals a 2 to the n. So given a and n, I could work out what a 2 to the n was. So that's the way we represent functions. This is the general form of the function. So this is the general form. And this is it where you've got an input of 2. So that's how the shorthand way of how you'd write it. So I'm now after the value of the function g when x equals 2. And that's how I write it. So that's one way we express functions, using this idea, and the function machine is the way we can think about it. Another way we can represent the function is to plot it. On the graph. And then we get a picture of what the function looks like. And an engineer will often do that because you want to see a picture of what's going to happen to this thing. So we fire up autograph, we can look at it. So we start a new page, we enter an equation, and we type in y. So this recognises y and x. So y equals a x to the power n. Yeah, okay. Now by default, this software using this constant controller here sets a and n as 1. So I can change them to any value I want. So at the moment, a and n are both 1. And so we're actually going to get a straight line because the power is 1. So it's just a times x. So we're going to get a straight line. But if I change the value for n, then I find that we don't get a straight line anymore. So if I change the value to n, yeah, I don't know quite why it's doing this. There's something weird about the function because it's not giving me anything to the left-hand side of 0 here. I'm not quite sure why. But if I were to actually type in y equals ax squared, in other words, I've set n equal to 2, I would get the curve the other side as well. So I'll do that in a minute. But we can use autograph to plot these functions. So what happens here is then we plot y equals ax to the n. And that's probably how you're more familiar with seeing a function, y equals something. But that's how you'd write it if you're going to plot it. And you're used to seeing y and x written like this. So x goes on the bottom, the independent variable, and y goes up the side. Independent variable, and this would then be the dependent variable. So this is a graph of y equals ax squared, so n equals 2. What do you think would happen to this function if I change the value of a? Yeah, so if I increased a, what effect do you think it would have? Yeah, that's right, because whatever x is, I'm actually making it a bit bigger by multiplying it by a bigger number. So y will be a bit bigger for any given value of x, so therefore it would be a bit steeper, a bit narrower, the curve. What would happen if I changed the value of the power? So instead of it being squared, it was cubed, and so on. What effect would that have? Let's have a look. Let's pause it. Right, and I'll sketch a few on here. It's not going to like it if I say x cubed. Any ideas why it's gone like that? So, what do you mean? Tell me, what do you mean? Yeah, so how come it's flipped down negative? I've forgotten a cubed, whereas it's positive if I'm x squared. Yeah. When I square a number, what's the answer always going to be? If I square a number, the answer is always going to be positive. So there's nothing below, y is never going to go negative if I square a number. If I cube a number, it can go negative, can't I? If I cube a negative number, it ends up being negative. Minus 2 times minus 2 is 4, times minus 2 is minus 6, so it will go negative. So this side flips downwards in a cubic. So that's sort of a classic cubic shape. There are lots of other shape functions that we can look at, and we'll see them as time goes by. The sine function, the exponential function, and we'll see the curves for them. And engineers are interested in the shapes of these curves. They're interested in finding out what the gradient of the curve is, and we'll be using calculus to do that. Some of you have already done some of that with me. They're interested in what the area under the curve is, so we'll use integration to do that. They're interested in what's the value of the function at particular points. So that's when you would either use a formula version of the function, i.e. you would put in a value. What is, if this was the g function, what is the value when x equals 1? And work it out. Treat it like a formula almost. Or you can plot the thing and then go up and across to find out what the value is. So sometimes we want values for the function, sometimes we want the gradient, sometimes we want the area. We're also interested in what happens as x increases. Y seems to be shooting off up, and that's not surprising as we're cubing it. What's the value of the function at 0? We're interested in all those sorts of things. Where does the function cut the y-axis? And so on. So we'll be playing around with these functions and finding these points. Engineers plot functions. We use these functions to model a situation, or to model real life. What does that mean? We use functions to model real life.
See what happened.
Yeah, right. Sort of to simulate, yes. To simulate a situation or something, to see what will happen in real life, to predict what will happen. Weather models, try and predict what's going to happen in the future. You wouldn't build a ginormous Airbus and then hope it flies. You would model it and check it's going to fly before you actually started building it. So you use mathematics to model situations and predict what's going to happen. And in electronics and mechanics, we'll be doing some of that sort of stuff in future units. We'll be using maths functions, predict what's going to happen in a particular situation, and then see what actually happens. Okay. Any questions on that? So now we need to look at these laws of algebra, which allow us to rearrange these formulae, having made this note here. The formula is a function expressed in a particular way. You can use these laws of algebra to rewrite the function. So what are these laws of algebra? Well, I'm sure you've looked at this sort of thing before. It's the idea of collecting like terms. The ideas of brackets, factorizing, expanding, expressions, the idea of the laws of indices that we've looked at in the past, but we'll remind you of them, or I'll remind you of them. Those sorts of things we need to look at now and remind ourselves of. Later on, we need to look at things like partial fractions. We talked about fractions, I think, in the first week, and I included them in the drill. So how do you manipulate fractions within algebraically, partial fractions? These sorts of things are in the textbook, and we need to remind ourselves of how these things work. So just have a look at this chapter and these 4 sections, 5.13 to 5.4.